So the next topic that we're going to be covering in class is accelerate motion. So we just got done in the last video talking about motion where the velocity is constant the whole time. And you guys did some calculations as part of your lab, or at least I hope you did. It's part of your lab on predicting the collision point for those two steel balls. And those equations are fairly straightforward, but that type of motion it's fairly simple, right? And it's a very limited type of thing where you don't have the velocity changing at all. So when we talk about velocity changing, we talk about something called acceleration. So when, let me get my cool pen here. Do green. So when we talk about acceleration, we define acceleration. So we're going to define that acceleration as the change in velocity over the change in time. Okay, so I'll call that acceleration. That's a vector as well. Now, here's the thing about acceleration is it's a little bit trickier. It's very, very tempting, and students do this quite often, to confuse velocity and acceleration. So let me kind of show you how things can be accelerated, some instances. So we have this idea of a car. I like cars. I just can't draw them. So there's a car, and the car starts at some velocity, and then eventually over here, it's going to stop and go to 0 meters per second, so it's going to slow down. And so this, very obviously, is a change in velocity. This is a change in the magnitude of the velocity. So the change in magnitude of velocity is, will produce acceleration, or I guess we would say the car experiences acceleration. Okay, so that's going to be acceleration. The other thing though that this car could do, if you think about it, and say it's going along the road, and we're going to kind of look at it from the top. So it's going to go along the road, and it's going to make a turn. So initially, we look at the car from the top, and it's going to have a velocity pointing this direction. Now, maybe in this case, we'll just assume the driver doesn't, hit the brakes or whatever. It just goes around the turn without changing the magnitude. So it's going to retain the same magnitude of the velocity. I'll indicate that by the same size arrows. And so the velocity vector has the same magnitude, but notice how it's changed direction. Now, as we said in the last video, there's vectors and there's scalar quantities, and velocity is a vector quantity. And once you get vector quantities, they have both a magnitude, like how big they are, and they have a direction. If you change either one, you've changed what the quantity actually is. So in this case, we have a change in direction, and this change in direction also causes acceleration. Okay, or the car will experience acceleration because of that. So the change in direction also equals acceleration. Now, I'm going to put a little, asterisk by this. We'll get to this later. Okay, we're not going to deal with this change in direction very much in this chapter. We'll deal with it a lot when we get to rotational motion. So really, we're going to kind of be focusing right there. Okay, we're going to be focusing at the change in magnitude and how we handle change in magnitude of the acceleration. Now, as I said, one of the issues with acceleration is confusing it with velocities. So to show you the difference, what we do is we have motion diagrams. So you imagine a car speeding up, and what a motion diagram does is, I'm not sure if you've ever seen those, kind of like, almost like the time-lapse photos where they overlap like the frames of a film with each other, and so you would see them all superimposed at the same time. So maybe at some point in time, the car is here and it's starting off and it's going 0 meters per second. And then 1 second later, it's gonna, it's gonna speed up constantly the whole time. So 1 second later, maybe it's right there. It's gonna speed up a little bit more, and 2 seconds, it's right there. Maybe 3 seconds, it's right here. Maybe 4 seconds, it's right here. Okay, and so at each one of these, you'll notice that the velocity vector has increased in length. Maybe I'll go off. Okay, so that is increased in length. And when we see this velocity vector increasing in length like this, what that's telling us is that our acceleration is pointing in the same direction as the velocity. Okay, so the acceleration always points in the same direction as the change in velocity. Okay, so the change in velocity is going, in this case, off to the right, and that would be the same direction as the acceleration of the car. Now, what if the car is moving already? Okay, maybe at time 0, the car is, moving at pretty quick, 30 meters per second. So it's going pretty quick, 30 meters per second, and then 1 second later, it's right there, and then it gradually slows down. Okay, slowing down, slowing down, slowing down. Okay, what you'll notice with this one is the velocity vector gets shorter and shorter with time. Okay, it's shorter and shorter with time. And so what that is indicating is that the acceleration is pointing in the opposite direction. Okay. Now, if I define my coordinate system, so if I say that this way is positive, in this case, I would say that my velocities are positive and my acceleration is positive. If I say down here, sorry, I meant your own arrow. If I say down here that this way is positive, then my velocities will all be positive, but my acceleration will be negative. Okay, so the car, this is what throws students, the cars can be moving in this direction, but be accelerating in the opposite direction from the way they're moving. Okay, and this is the case where you'll see that is when the velocity is decreasing, the magnitude of the velocity is decreasing over time, then the acceleration has to have an opposite sign from what the velocity is. All right, so how do we do calculations? How do we calculate the things we want to calculate, namely time and displacement and velocity, if the velocity is constantly changing? And the way we do it is we use these things called the kinematic equations. Now, I was really tempted to derive these for you guys. It's a lot of fun. It involves graphs. It's a, blast that's had by all. But really what's important is that you guys can use them to do calculations. So I'm going to show them to you here. You will always be given these equations on tests and quizzes. So please, 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 please do not memorize these. You might end up memorizing them because you're going to use them so much, but these will be provided to you. You probably want to copy, well, you do want to copy them down so you have a place to look for, like one spot to look for when you're working homework problems. But don't worry about memorizing these equations. But you'll see for each one of these are only true if the acceleration is constant the whole time. If the acceleration is changing, the magnitude of the acceleration is changing, then we have to use calculus, okay? And that's what AP Physics C does. That's not what we do. And you also notice that in each of these equations, something is missing. So in this one, the displacement's missing. Okay, so this is kind of like a missing thing, right? So the displacement's missing in this one. In this one, what's missing is our final velocity. Okay, so kind of defining terms here. This v naught is initial velocity. This v is my final velocity. I can't get the final velocity with this equation. And this one, the time is missing. Now this one's kind of useful because if you don't know what the time is, but you know what your displacement is, you can use this equation. And then this is the definition of the average velocity. So when we work problems with accelerated motion, what we're going to do is we're going to look at what do we know and what do we need to find. Just good, solid problem-solving technique. And then we're going to look at these kinematic equations and we're going to pick the one that allows us to solve, that has what we know in it and allows us to solve for what we need to know. And as always, it's easier to show, or at least better to show, than just to tell you guys. So here's a problem. And what I'm going to do is I'm going to take you through the problem-solving process that I expect you guys to use on all problems that you solve in this class. So you can see the problem above. It's a world-class sprinter. I thought, hey, the Olympics, right? It's kind of apropos. The first thing that you want to do is you want to make a diagram. So we'll call that D. And in this diagram, we're going to, just kind of do your best. And no one expects you to be like an art major here, right? But just do your best to kind of represent what's going on here. So we have a sprinter, okay, and she's running along and she goes a distance. So on this diagram, I'm kind of marking stuff down. She goes through a displacement of 18 meters. Okay, so part of the job that you have is to interpret these numbers in the problem so that we can translate them into equations. So when you see 18 meters, we see meters, those are displacements. Also, a top speed, when it says top speed, that's essentially telling me that that is my final velocity is 11.5 meters per second. Also, you think about a race and how a race occurs. The sprinter started off at 0 meters per second. The problem never tells you that. You have to kind of, interpret that. So the diagram is the first thing that you need to do. And you think about the sprinter and you think about her motion diagram. It starts at rest and then, wow, sorry guys. It's going to get further and further. So these dots are going to get further and further and further away. Okay. And further. Okay. So the idea is that these velocities are increasing with time. And so her acceleration is going to be pointing in the same direction. And we also have to define our coordinate system. This is critical, critical, critical. We need to define which way is positive. And yes, you should write an arrow with positive to remind yourself of this, or else you will eventually mess up the signs of these variables and you're going to get problems wrong. All right, so this is all about the diagram. Draw a diagram, label some stuff, motion diagram, label your coordinate system. Okay. Then we have our knowns, so K, so we know what the final is. We also know what the total displacement is. Okay. We know what our initial is. Okay, so we know all that. Our unknowns, we don't know what, this is what we're asked to solve for. We don't know the acceleration, and we don't know the time. Okay, so your diagram, your knowns, your unknowns, and then we think about the equations. What equations are we going to use to solve this? So going back to the kinematic equations, I know the final velocity, I know the displacement, I know the initial velocity, and the final acceleration or time. So looking at these, I can solve for, let's see, I don't know time, so this doesn't really help me define acceleration. This one will, though. I don't need to know the time. I can solve for the acceleration using this one. So notice that this has everything I need, these velocities, the displacement, and it also allows me to solve for what I want. So with that in mind, I'm going to use that equation. So I'm going to say v squared equals v naught squared plus 2a delta x. Okay, and then once I know the velocity, I can use the other kinematic equation. I can say that v is equal to v naught plus acceleration times time. So I have my equations, and then the last step is going to be to solve. So I'm going to solve for acceleration. Okay, solve for acceleration. So this will be v squared is equal to v naught squared plus 2a delta x. And you should always rearrange your equations before you plug in numbers. So then I'll plug in my numbers, 11.5 meters per second squared, minus 0 meters per second squared, divided by 2 times 18.0 meters. And so I'm going to have 3 sig figs because I'm dividing and all my numbers have 3 sig figs. So to 3 sig figs, my acceleration will be 3.67 meters per second. I know all my velocities are positive, so my acceleration will be positive. I know my acceleration should be positive because of up here. Then, knowing this, I'm going to solve for time. V is equal to v naught plus at. Solve for time. V minus v naught over a. Plug in my numbers. Sorry, 6.7, and I get 3.13 seconds for my time. And there you go.